All right. Welcome to lecture 2. We're going to do inheritance today. But first, I want to do the prisoner dilemma tournament. Let's see. Yeah, let's just go ahead and jump right in. And, so first of all, I made the due time for the prisoner's dilemma assignment at 12:30, and then I found out that I actually can't download any of this assignments if peer grading is on them until after peer grading has ended. And then I found out I couldn't take that off. So I just had 20 minutes since like 12:40 to be able to actually like try running all of your code and seeing if it works. I got it to work, but if your file threw any kind of error at all, then it didn't get included. And I have not tested this code at all. I just barely got it working just now. So if you don't see your prisoner in the output, like it's possible that my script was just a little too aggressive in trying to eliminate errors. So don't get offended if you don't see your prisoner. I'm sure everybody did fine on the assignment. I guess I kind of skipped over it in the first lecture, but this is a 1 credit, no credit student talk class. So it's not like this is going to be very harsh grading or anything. And that's kind of why I want to do peer grading. It's really, the whole point of grading for me is just to get another set of eyes on your work. So that's why I want to do peer grading, is just so that those set of eyes can be each other. It's also much easier for me. So, but I have to figure out how that's going to work, since Colab isn't going to be very friendly. So stay tuned. Peer grading instructions will come. But just like the grading on regular assignments, the peer grading, is also pretty chill. I just want you guys to look at each other's code. So, okay. I've got the results here. First off, if it's a -1, then there was some sort of runtime error. So there's some sort of runtime error here. Again, this could be my script being overly aggressive and trying to be safe. But the first non-1 score here is Jesse. Hey. So that's the best score, right? Because this is number of years in prison. So congrats. Do you want to tell us what your strategy was?
What my strategy was?
Yeah.
Basically, I was cooperative until I got betrayed, and then I just stood up bully, and I was like, "If you've been betrayed before, just keep confessing and screwing over the other person." All
right, cool. So the first sign of any kind of betrayal, and you just okay, cool. Well, yeah, that seemed to work out pretty well. A lot of these scores are exactly the same, and that's probably because you did the exact same strategy. Which is fine, because there's only so many ways that, play the prisoner's dilemma. So Jasper, you got a Jasper here?
That's me.
Oh, no way, right next to each other.
Yeah.
What did you do?
I checked if, I was looking at I was trying to figure out the chance that the other person would pick the worst, or the chance that the other person would pick the thing that's better for them, and then pick the thing that was better for me.
So you're trying to think one step ahead, basically.
Right.
All right.
I guess that didn't work out too well.
Yeah. Turns out people are unpredictable, I guess.
Yeah.
Well, so I said I don't know if I put it in the assignment, but I wanted to incentivize people trying crazy strategies, so I said I'd give extra credit to the best and the worst, so you guys got it. You guys, would you mind if we pull up your solution, Jesse?
Go for it.
No? All right, cool.
It's already there, isn't it?
Oh, wait. Oh, shoot, I already pulled it up. Sorry. Yeah. I was going to ask your permission first, but did not. So, yeah, like I said, the reason I don't have a late policy is because I want to go over the homework at the beginning of the next lecture so that we all just kind of stay on track. So this is me going over the homework here. So The decide method was pretty simple. Basically, you just have to return a Boolean. It's as simple as your strategy is here, and this strategy is pretty simple. So it just checks if you've been betrayed, and then if you have not been betrayed, then shut up. If you have been betrayed, then return something. But the question is, how do you know if you've been betrayed? You need to keep track of some state. And so what I kind of was trying to get people to do, but not actually, it didn't say you had to do this in an assignment, but any kind of reasonable strategy is going to want to remember what's happened in the past. And that's why this function existed. It was so that you could take in the number of years that you were sentenced and then remember something about it so that next time you could inform your decision. So, you didn't have to do that. It was perfectly valid to just write a strategy that didn't require any state. But, I was trying to come up with, a class where some state might be useful. So here, the state that was added was self.betrayed. And it looks like if betrayed, then we don't worry about updating the state. But if we haven't been betrayed yet, which is the default, then we check if the years is equal to some sort of betrayed state, and we change the instance field. So yeah, this is exactly what I was hoping people would do. Again, it doesn't matter really what your strategy was. If it didn't require state, that's no big deal. But yeah, questions about the homework? No? Cool. I hope that was fun. I don't know. I hope, should I post the results? Do you guys care? Like how well your prisoner did? Or not so much?
Sure.
I'll post them. Because I know I went like through the list pretty quick, so I'll post those results if you're curious. But anyway, let's go back to the slides.
Can you give results with filtering out the rats?
Filtering out the rats?
Like if someone always says always rats out, just omit them from the comparison.
No way.
Okay.
That's life, people rat.
I think it says that we may want to simulate the real life, maybe removal of those rats.
Oh, you're saying like you're in a gang or something and you don't let snitches in your gang? So you would only be committing crime with people who would shut up. That's a great way to win the prisoner's dilemma, but kind of not really, because in real life you can't eliminate all the snitches. So, who here just always snitched? Only one person, so there you go. See?
Almost always.
Almost always? Who here almost always snitched? Alright, cool. Who here did the assignment? Alright. Alright, so that was fun. And today we're going to continue going over object-orientedism in Python. And so the next thing is inheritance. And I know you probably think you know inheritance, or even if you don't, then that's fine. But inheritance in Python gets very, very weird, as we'll see. So the syntax is not weird, though. Basically, if you want something to inherit, then what you do is you put the thing that you want to inherit in parentheses after the name of the class. Pretty straightforward. And so now, student is a subclass of a person. Any given student is a person. That's the is-a relationship that you learned about in 2110. So if we make a student now, we know that we've inherited from person because this string method got called. So the fact that we printed out this student and it printed out like this is kind of proof that we did actually inherit that string method. But then we added some new methods like .report, and so that works too. But if you tried to call .report on an instance of just person, that wouldn't work because the person doesn't have report. One thing to note here is the way you call your super method is with a function call to super, and then you just tack on whatever else you need. We'll come back to super because it's not nearly as simple a function as you might think. We can also explicitly inherit from object. That's what happens if you don't include parentheses after the name of your class. So if you just say, like with the top person class there, colon, without parentheses, no classes, then you're implicitly inheriting from object. And then the one other thing here is, instead of calling the super and then calling your method, the other thing you can do is explicitly reference your superclass. So here, we're explicitly saying, look, I know who my superclass is. I'm going to call this init function. And this is an example of what I briefly mentioned last time. This is a static reference of a method. So you have to pass in self here, whereas here you don't have to pass in self, because super actually binds the method. Questions about this? Let's get 2 questions.
What if it's not your superclass?
What if this isn't your superclass?
Yeah.
Great question. Totally allowed. You can call any method here. So, in fact, you can call your subclass. In this person class, you could say, let's say, like you want to actually borrow some functionality from some subclass of yours, some specialization. You can totally do that. You can call, this could be something completely unrelated. Yeah, good question.
Can you do multiple inits?
Multiple inits? Yeah. Yep. Because this init function, just like how you can call it on any class, you can call it multiple times on any number of classes. So like, let's say this student class is actually very similar to some student class that somebody else has written at some point, and you think you can just straight up call their init method and it'll work, then you can do it. But the odds of that working are pretty low. But you can do it, yeah.
I printed the type of super. It's a class type.
Yeah,
What's the other?
we'll get to it.
So if you wanted to print like I'm blank a student, so you want to use some of your super classes thing,
But not all of it.
onto it, what
Yeah.
are you using?
So you're talking about overriding the string method here in student, right?
Yeah, but you want to like use what it already has,
And you want to insert like student in the middle here,
or just like after it.
or after it. So doing it after it would be not too bad. Because what you would do is, yeah, you would basically call, like, let's say we're in a string method. You would call super dot thunder string, and then you could just say right after that plus whatever you wanted to tack on and return that. If you wanted to put it in the middle, that would be a little trickier. I think you would actually have to parse this and split it by space or something, and then manually insert. But the idea is the same. You call super on whatever method you want, and then you can make changes. You can append stuff and then return the changed version if you want. That's no problem.
Would it stop you from in person saying then calling a student in your init and then like infinitely going back and forth?
Nope.
No.
No, there's no checks there. It's very easy to get into infinite recursion with this. In fact, I meant to mention, this is pretty discouraged. Don't do that. Because, well, first of all, it's not very clean. The fact that we've had to say person twice here. You know, we've already declared that this thing inherits from person. So we shouldn't have to say person.init again. So that's one reason right there that you shouldn't do this. But then also, yeah, like person init, you can get into weird recursion things here and get into infinite loops.
So you don't have to call super as the first line in the constructor like you do in Java.
No, great question. Yeah, in Java, it forces you to call your super constructor as the first line of your constructor. It's a pedantic thing, but it has to do with how objects are created in Java. You don't have to do that in Python.
So does that mean you have, but to use the things that are in your super classes, like fields, basically, you have to call super before you use
Yep.
everything?
Yeah, so calling super init here set up our name. So if we tried to reference self.name before this call to super init, it wouldn't have worked because we hadn't initted the super yet. So yeah, that does become tricky. Other questions? That was like way more than 2. All right, let's implement a quick diagram here just to like check that we're on the same page. Let's do this half first. We've got class A inherits from object. Again, that's optional. Class C inherits from A. Class D inherits from A. E inherits from A. And now if we wanted to like just check, sanity check that we've done this right, we can check the bases of C. And what do we expect? It's actually not so obvious what we expect. What do we expect C dot bases to be?
A list containing A and object.
That's what you might think, but it is just the direct super. So the base classes are literally what you put in this parentheses. So C bases is just A.
Why is it plural then?
Sorry?
Why is basis plural then?
All right. The other half of the diagram, exception is a built-in class, but we can extend it anyway. So we've got a myException extends exception, and we can make it called a super, and then we can raise that exception just like I would expect. So now we've implemented this whole diagram. Pretty simple, but yeah. Any questions? Okay. So suppose we call c.foo. Which foo method do we call? Let's say like all of these classes contain a foo method. Which foo method do we call when we call c.foo? C, yeah. We should hope it's C, right? Because that's the most specialized version of the foo method. You know, if we were dealing with an instance of C, and we call foo on C, and C defined foo, then we better call C's foo. But what if C didn't define foo? Then which version of foo do we call? A, yeah, we look up the tree. So we look for C, we look in C first for a method foo, and then we look in A, and then we look in object. And that's kind of intuitive. That's the intuitive way that inheritance works. We start looking for the most specialized version, and then we go up the tree. In Python, we give that concept a name, the MRO, method resolution order. So whenever we look for a method, we look in the method resolution order. So here the method resolution order for C would be CA object. And this works because it's a tree. We can just go up it. Does that make sense? But as some people noticed, I said superclasses, super usually means, and this is confusingly called bases. These are all because Python allows us to do multiple inheritance. So let's just give it a try. Just like how we did before where we tried to implement that diagram. Let's implement this diagram. First off, we've got A inherits from object, we've got B inherits from object, C now inherits from A and B. So if you want to do multiple inheritance in Python, you can just comma separate the classes that you want to multiply inherit from. Class D inherits from B and A. Note that I changed the order here. Do you guys think that matters? Yeah, it definitely matters. And in fact, we'll see that it actually causes problems here. And then we define class E. And what do you guys think is going to be printed here? What do you guys think is going to happen? Nothing? Probably nothing, right? Or sorry, here. What's going to be printed here? What are E's bases? C and D? Nope. This doesn't work. We actually get an error here. So I'm sure you're confused as to why. So in this scenario, suppose we call E.foo. We need to find a version of E to look at, and we definitely look at E first, right? But then where do we look? Let's say E doesn't define foo, and where do we look?
Does the order, it would either be C or D, but does the order matter? That
Yeah.
C and D are in, and that decides which one's first.
Yep, so this is the first instance where the order matters. We define E as a subclass of C and D, so we should probably look in C first. That does make sense. But then where? Then where do we look?
Does it go breadth first or depth first?
Breadth first or depth first? Well, which makes more sense?
Breadth first.
Breadth first? Really?
Yeah, because we have to know C.
Breadth first.
Mm-hmm.
So do we have to initialize C after D inside the init of D?
We'll get there. Yeah, the order does matter, but there's a built-in Python thing that deals with that for you. Yeah. So some people are saying breadth first search makes more sense here, as in D, right? You're saying D. Yeah, I'd be inclined to agree. You could call it ambiguous, but let's just say that it is D. Let's say we look at an E and then C and then D. Then where do we look? A. Why A? We go back to C and we look at A. All right, so let's say we visit A. And then where? D. So here's the problem. We just defined D as inheriting from B and then A. So we didn't follow D's instructions here. D said, I shall first inherit from B and then A. But we just looked at A and then B. So I'd say there's ambiguity at several levels here. Either way, it's clear that we need some sort of algorithm here to figure out the order of things that we look in. We had a couple of candidates, depth first, breadth first. But it turns out Python uses neither of those things. Python does have an algorithm to figure out what the method resolution order should be, and it's called C3 linearization. So I'm going to call the linearization L. We need to define some subfunctions here first. So let the head of a list be the first element of the list. The tail of the list to be everything after the first element. And the merge of a sequence of lists, let it be to find the first head that is not the tail of any other list, append it to the output, remove it from the inputs, and repeat. You guys don't have to write this down and memorize this or anything, because it'll be in the slides. So given those subfunctions, the linearization is the class that we're trying to compute the linearization of. That makes sense, right? Because we always look in the class that we are first. We always check the bottom first. So this is the bottom. This is the class that we're trying to find a method resolution order of. We always start there. And then if that doesn't work, we merge the linearizations of the superclasses and the superclasses themselves. So this is an algorithm for finding the MRO and multiple inheritance. So let's compute L of object. It's just object, right? Because object doesn't have any superclasses here. So we get the class object itself, and then we merge nothing. So it's just object. What about the linearization of B? Well, we start with B, and then we merge the linearization of the superclasses and the superclasses. So the linearization of object was just object. And then we have the object superclass here. So that list of lists would look like object and object. Right? And then the merge is that we find the first head that is not in the tail of any list. So here's the first head, object. Is it in the tail of any other list? No? So we output it to the output list. And then we remove it from all of the inputs. And we're done. We've merged everything. So the method resolution here goes B plus object. Yeah? Starting to make sense? Okay, how about C? So the linearization of C is going to be C plus the merge of what lists? It's going to be A object, B object, and then the superclasses themselves, A and B. So we're merging those three lists. A object is the linearization of A, B object is the linearization of B, and then these are just the direct bases. So we're merging those. So we look for the first head that is not in the tail of any list. A is not in the tail of any other list. So we put A in output, and then we remove it from all inputs. Alright, now we look for the next head that is not in the tail of any other list. You got object. Is object in the tail of any other list? Yeah, object is still in the tail of this list. So we don't look at object. Object is not the next thing. So we go to the next head, B. Is B in the tail of any other list?
Yeah, not anymore.
Not anymore, because we deleted A. We put B here. We put B. Now we're left with just one class object. So it's an object. So we should get CAB object. Yep, CAB object. Okay. Questions about the C3 linearization so far? I know this is kind of obtuse.
Why is it called C3?
I have no idea. Yep. Okay, let's do D real quick. It's the merge of the linearizations of B and A and B and A. And the linearization of B was B object. This is A object. So this is very similar to the linearization of C, but we basically kind of switched the orders of B and A. So it's DBA. You look in D first, and then instead of, before it was CAB, now it's DBA. And that makes sense because we switched the order of B and A for our class D. Okay? Okay. Finally now, what's the linearization of E? What's the merge of the linearizations of C and D and C and D? Which is the merge of CAB object and DBA object. So let's go through here. We're trying to find a head that is not in any other tail. So C is C in any other tail? No. So we're going to delete C. And C goes to the output. So now we're looking for a new head that is not in any other tail. A. Is A in the tail of any other object? Yes, it's right there. Right? A is now the new head of this list. But it's not a candidate for going to the output because it's in the tail of this list.
Why we skip over the object?
Why do we skip over object?
Isn't the object in the tail?
It hasn't been ahead yet.
Yeah, we go through the heads looking for a head that is not in any other tail. So object isn't the head yet. We've got C, A, B, object, D, B, A, object, and C and D. Alright, so we said C works. We put C in the output. And now we look at A. A is the new next head. And is A in the tail of any other list? Yes. So we can't use A, so next head, D. Is D in the tail of any other list? No, because it's not the head of this list. So we've got D. D works.
And then you don't have one.
Yep. Now we've got a problem. Because we're looking for the next head that is not in the tail of any other list. So is A in the tail of any other list?
Yep.
Yep. Is B in the tail of any other list? Yep. So what do we do?
Throw an error.
Throw an error. Yeah. This class inheritance diagram is considered too ambiguous. Python does not know how to linearize a method resolution order here. So what really would have happened before when we were defining all those classes is as soon as we got to class E and we tried to define it with bases C and D, we would have gotten type error, which is weird because you don't usually think about getting an error right defining a class. Usually you get an error, like a syntax error when you try to load a file, or you get a runtime error when you try to like instantiate this class. But no, this is a class definition error. This class does not define. And it's because it's considered too ambiguous. We don't know how to look up methods on instances of that class.
You only get that with E, right?
Yep.
So up to C and D.
Everything else would have worked fine, yeah. But as soon as you try to define this base class or this class E, Python is like, this is too weird now.
It's for solving Python.
Let's see. Okay, other questions about this? This is confusing. So I'd say 3 questions.
So when is C3 linearization different from just doing a breadth first search? Like what type of tree structure would generate a different output?
Honestly, I'm not totally sure. Different than breadth first or depth first?
Breadth first.
Breadth first.
I guess
I don't know. I'd have to put some thought into coming up with an example, but there definitely is an example. I mean, it's not as simple as breadth first search because otherwise they would have just implemented breadth first.
Yeah. Is it that C3 linearization like explicitly detects ambiguities, whereas breadth first search won't really care?
Yeah, correct. So C3 linearization has there's 3 properties that it tries to maintain about the method resolution order. It tries to maintain that you always search in the order that the base classes are defined in, which is what I was getting at before. C defines A and B, and D defines B and A. And so that's actually why this failed, basically. C3 linearization is designed so that if D is in this diagram, and D defines that it goes B and A, we never look at A first and then B. So it tries to keep that consistent, and it couldn't keep it consistent here. Yeah. And there's a couple other things it tries to maintain. I don't remember them off the top of my head. Okay. Other questions about this?
Do any other languages use C2 in their organization?
Great question. I don't know. Not many. I mean, not many that are really used, partially because multiple inheritance isn't allowed in very many languages. Yeah. Other questions? No? C3 linearization just makes sense?
Is multiple inheritance useful?
Ooh, great question. I think so, and so I'm gonna pull up some code here in a sec. Some code that I wrote yesterday that uses multiple inheritance for a real project, no less. Not even a dumb example. Other questions? It's okay if you don't totally remember the exact details of the C3 linearization algorithm. But what's important here is that you remember that there is an algorithm that tries to compute this order at class definition time. And then that order is locked in, and it's very important. So we're going to see why it's important here in just a second. We need to resolve super, because super kind of seemed like it was just looking at your superclass, right? But how does that work if you have multiple superclasses? Like, which one? Well, we just talked about this method resolution order. Turns out that super uses the method resolution order. Super does not really mean superclass. In fact, it's kind of a misnomer. What it really should say is next in the MRO. It should be called next. The problem now is though, which MRO? Because we just saw how every single class in that inheritance diagram had a different MRO. So what MRO are we talking about? Do you guys have any ideas?
Classical superin.
The class you call superin? That's what you might
Would make
think.
sense.
That's what you might think. But the problem is that we just saw how the method resolution order can change depending on how deep you are in that class inheritance tree. And so we might be in a certain class, but really an instance of some deeper object. Like let's say we're an instance of E in that previous example, but we've called super a couple of times, or somehow we've ended up in a super method. Then it's not so clear if we should talk about the super of that class that we're literally in, or the super of the class that we started in.
Can you repeat the question again?
The question is, which MRO? Every class has a different MRO, even if it's in part of the same inheritance tree.
Does the super use?
Which one does the super use?
Can you like use the same thing but go from backwards? Like start from object, then do whatever before, then do that, like do the initializations like that?
You could, but that would be very weird because you'd be starting with the most general one and then going to the most specific. But even more importantly, like which list are you even looking at? Okay. So let's take this inheritance diagram here. This one's a little simpler, and we'll see what I mean. Who is B's super? It kind of seems like it should be A, right? But basically, that question doesn't make sense in Python. Python doesn't really have a sense of like, oh, B is A's, or A is B's super. And to prove that point, let's take this inheritance diagram here, where we've got class A on the top, it defines a foo that prints A. B has a foo that just calls the super foo. So we're going to see very well here who is B's super. We're going to call it and it'll print something. D, it prints D, and then C defines nothing. But it inherits from B and D in that order. So if we call B.foo, what do we get? Who says A? And who says D? Who says something else? Nobody says anything. We get A. Yeah, and that shouldn't be surprising because B, we have an instance of B here, and we just call it foo on B, and B goes up to A. But now let's call foo on C. It actually prints out D. So what happened here? We were in class C, we had an instance of C, and we called foo on it. We had to find a definition of foo somewhere. We didn't find it in C because C doesn't define anything. So we look in the next MRO, the next class in the MRO. What's the next class in C's MRO?
B.
B. Yeah, so we look in B. B, we found a foo method. That's great. So we call that foo method, boom. What does the foo method do? It calls super.
The next one is C's MRO.
Super gets you the next thing in your original MRO, which is D.
Why is it still C's?
Because super takes in, so yeah, that's a great question. Basically because that's what we want. We want, I forget who asked the question earlier, but the question was about the order of inits and like how do we know what order to call all the inits in? Python solves that for us with this super. If we always call super.init, super is going to guarantee us that we call every single init above us. So if it didn't use C's MRO and it used the class you were in's MRO, super here would go to A and we would have skipped D's init function or D's foo function. That doesn't make sense. We said we wanted to inherit from D here. We better hit D. But how can we if we're in B and we don't even know about D? Well, super. Super is a very cool function that knows about the MRO of your original starting point and will make sure you get there. Is that weird or what? So if you ever find yourself asking who's B's super, that's not a question in Python. It would be a question if we change this to a lowercase b and we said what class we were in, right? So, like, instead of saying who is B's super, we should have asked, hey, I'm a C, and I'm currently in class B. Who is my super? And this should look familiar if you've written old versions of Python. If you've written Python 2, then you'll remember that in order to call super, you actually needed to pass in B and C. Self, basically. You would always write, whenever you called super, you would pass in the class that you're in and the thing that you are. And that was because that's essentially what super needs to know in order to figure out where to go. Super needs to know where you started and where you are, and then it can tell you where you should go next. But eventually in Python 3, they optimize it so that you don't need to pass in those things.
Can you tell me why it works like sort of as expected if you switch the class declarations around for D and C?
If you switch the class definition around on B and C, say that again?
Yeah, so if you switch the order that they're defined.
So if we had defined C first and then D,
Yes. Then.
that wouldn't have worked because D wouldn't have been defined, so it wouldn't have been inherited.
Oh, well, I'm reading from just like one script, so. Yeah, so I guess in a shell, it just goes on, but, I just have it all in one file, so when I run it, it's like.
You switched the definitions, and so you hadn't defined D yet, but you were able to inherit it? That shouldn't work, I don't think.
I might have had something like, let me just switch it around.
Okay, I don't think that, if that worked, then I need to study some
It
Python.
might have just been because I had, yeah, it's different.
Okay, cool. Uh-huh.
If you define in class C, D, then B, would it not touch B since it can do food and D?
Yeah, great question. You're saying if we had switched this, right? Yeah, if we had switched this and gone D and then B, then we would have checked D first, and D doesn't call super. So that's kind of a pitfall of this design pattern. We said super, super nice. Because it'll guarantee that we get everywhere we need to get in order to satisfy original starting point MRO. That's not true if we forget to call super. So that's a really common bug where you're inheriting, you call super, all the classes you've written call super, but like some class that you're inheriting from forgets to call super, and then that kind of throws everything off.
So then also, if you were to do like def food in class B, after you just have that like super dot food, if you were to say print B if you did it in the original order you had it.
So original order, right after this we say print B,
Yeah.
then what would have been printed?
We would print like D then B.
Yep.
If you wanted to call super in both B and D.
Other questions about this? So I said that super needs to know the thing that you are and the place you are, right? But how does it know? How does it know where we were and what we are? We didn't pass in these things. We didn't pass in self and the class that we're in. So how did super know which MRO to talk about? It's just a function. We just call it a function here. So does anybody know?
Does it resolve at runtime? Is that the object? The type,
That's exactly what it
type
does.
stuff?
That's exactly what it does. So the MRO is calculated at class definition time. So we've got, for each class, we have a list that represents the MRO. What super does is, it actually does some crazy meta stuff. It checks, first of all, it uses reflection to figure out what class you're in. Turns out in Python you can reference this variable dunder class, and that'll refer to the class that you're in right now. So that's meta thing number one. And then meta thing number two is it has to get self, right? It has to know what you are. So it has to get self, but this is just a function call. Any guesses on how it does that? It peeks at the stack. The first thing at the stack is self. So super peeks at the stack, and then references the dunder class attribute, and then it has everything it needs in order to figure out what to look at. So is that crazy or what? So I said that that's metaprogramming, but only kind of, because it turns out that super is not written in Python, it's written in C, and so arguably it's not meta because it's the interpreter. The interpreter is doing that, so of course the interpreter has access to the stack. But I would still argue that that's metaprogramming because interpreters are metaprograms.
Does super need to be the first, or can it be anywhere?
Can be anywhere.
Okay. But in that case, wouldn't the stack change, or no?
Good question. No, because local variables aren't stored on the stack.
Oh, right.
Not in Python.
Right.
Okay. So just to put some real life context on this, I want to pull up some real code. First off, somebody asked if, this is our capstone project, so some people are real triggered right now. But some people asked, like, is multiple inheritance even useful? This is an example of multiple inheritance that I use. Can everybody see that? Let me make that bigger. Now it's all right. Can everybody see that?
Yeah.
No? Okay. How about now? Better? Okay. So this is a class that I wrote, and I called it Mixin. And that's actually a design pattern that uses multiple inheritance to work, to operate. Mixin is basically a superclass that you don't intend to have the is-of relationship. So I wrote this class here basically to be able to include this function in a bunch of subclasses. But I don't really, a subclass of easy import mixin isn't an easy import mixin. I just wanted to include that function. So here's a place where I use it. Legacy user imports model.model and easy import mixin. Now you might ask, like, well, why didn't I just make easy import mixin inherit from models.model, and then I wouldn't have to inherit from models.model here? Okay, that would be kind of the standard way you would solve this in Java, is that you would make this inherit from that, and then this would inherit from both, because it's all part of the same tree. The reason I didn't do that is because this is actually a very, very special class that does things when you subclass it. If you've written any Django, then you know that if you create a subclass of models.model, you're really creating a SQL table. I did not want to be making a SQL table, I just wanted to be including some functions in some of these subclasses. So it's actually very important that I separate these two things. So I can't have this inherit from that, but I want this to inherit from both. And so this is a perfect example of the mix-in design pattern, and it's one scenario where multiple inheritance is really useful. You might be asking, how does this work that it actually creates a SQL table when you subclass it? That's pretty weird. Well, we'll get there. Because it turns out that models.model has a custom meta class that knows to do things upon being subclassed. And so that's actually a great thing to look at if you want an example of some crazy metaprogramming that we're going to do later. But for now, this is an example of multiple inheritance. The one other thing I had was, first off, so here we have the super function. First off, it turns out that it's a type, and so super is not a function, it's actually a class. So when you call super, you're actually creating an instance of super object. And then that super object does some stuff to look up, check on the stack, figure out who you are. But it's all implemented in C, so it's actually really hard to read. But if you like C, and you want to get into this kind of stuff, people will sometimes forget that Python is just open source, and so you can just look at the source code. So there it is, that's the super class. It doesn't make much sense because of esoteric Python things, but you can look at all of these functions. That's a really interesting one if you're curious. And then finally, the author of Python wrote this great blog post on super when it was introduced to the language. And he wrote this kind of Python equivalent version of super. So if you were to write the super class in Python, this is what it would look like. So I might send out these links in an email or something, but this is really interesting if you're still interested in super. It's a very interesting metaprogram. Yeah, so there you go. All right, good luck on the homework. I forget what it is, but oh, it's the bomb one. It's the bomb. This next homework is fun. Definitely do it.